In our previous video, we saw objects falling freely under gravity are free from their masses. Objects being massless, big or small, hollow or solid, fall freely each at the same rate of acceleration. But the value of acceleration on the surface of Earth is constant as E equals 9.8 meters square. Hence, Newton's equations of motion can be applied to vertical motions, like we apply to the horizontal motions. For that we may write Newton's equations for vertical motions, replacing A by G. For example, V equals U plus GTS equals UT plus 1/2 GT square and V square equals U square plus 2GS, where U equals initial velocity, V equals final velocity, G equals acceleration due to gravity. Here, G is considered positive when the object falls freely under gravity, and negative when the object moves above the ground against gravity. Let this is a body of mass m. Total amount of substance contained within is called its mass. As we know, mass of a body is the measure of its inertia. Greater the mass, greater is the inertia. It is this inertia of mass that always opposes any change. Or we can say mass of a body always remains constant. For example, if the mass on Earth is 50 kilograms, will remain 50 kilograms on Moon, or anywhere in space. In order to understand weight, let us have two bodies of mass m and mass m. There exists a force F between them. If me is taken as mass of Earth attract mass m towards itself. An acceleration produced is g.so. The force applied by Earth on mass m is F equals ma. But for vertical motion A is replaced by g. We will call this force as weight of the body, written as W equals mg. Therefore, total amount of force by which the body is attracted towards it, called its weight. SI unit of weight is Newton N. 1. Two objects of different masses falling freely near the surface of Moon would a. Have same velocities at any instant, b. Have different accelerations, c. Experience forces of same magnitude, d. Undergo a change in their inertia. Since the objects are falling freely have same velocities at any instant, so answer is A. 2. The value of acceleration due to gravity, A, is same on equator and poles, B, is least on poles, C, is least on equator, D, increases from pole to equator. As we have seen before, the value of acceleration due to gravity is maximum on poles, and decreases towards equator, so the value of g is least at equator. Answer is C. 13. The gravitational force between two objects is F. If masses of both objects are halved without changing distance between them, then the gravitational force would become AF4 BF2 CF D2F. Let m and m be the mass of two objects, r distance apart away from each other. Let F is the force between them. Then F equals gm upon r square. 1. Now if both masses are halved as m upon 2 and m upon 2, r remains unchanged. New force F equals m upon 2. M upon 2 upon r square equals 1 upon 4 mm upon r square. Equals 1 upon 4 F. From 1, hence new gravitational force is 1 upon 4 of F. Answer is A. 3. In the relation F equals gmm upon d square, the quantity g, A, depends on the value of g at the place of observation, B, is used only when the Earth is one of the two masses, C, is greatest at the surface of the Earth, D, is universal constant of nature. When two unit masses of this universe are places unit distance apart, then F equals g1 guna 1 bata 1 varg equals g. Hence, the nature of g is a force, similar throughout the universe. Hence g is a universal constant. Answer is D. 5. The weight of an object at the center of the Earth of radius r is a 0, b, infinite, c, r times the weight at the surface of the Earth, d, 1 upon r square times the weight at surface of the earth. As we know weight of object, W equals mg since g at the center of earth is 0. Hence, W equals 0 weight of object is 0. Answer is A.